Okay, so I think if we can start. Good morning, everyone. Welcome to the ESIC seminar. Today we have our speaker, Dr. Noel Schulz and Dr. Vincent Sprenkle. It's my pleasure to welcome them to the ESIC seminar. They'll be speaking to us about US-India collaborations for advanced distribution systems and microgrids, including renewable and storage. I'll briefly introduce our speakers today, and then we'll start with the presentation. So Dr. Noel Schulz is the Edmund O. Schweitzer III Chair in Power Apparatus and Systems with the School of Electrical Engineering and Computer Science at Washington State University. She has been a chief scientist at Pacific Northwest National Lab since February 2020, serving in joint appointment as a part of PNNL WSU Advanced Grid Institute. In August 2021, she became co-director of AGI. She received her BSEE and MSEE degrees from Virginia Tech and PhD in EE from University of Minnesota. Dr. Schulz has been active for over 26 years in teaching, research, and service at 6 universities. Her research interests include power computer applications and power systems planning and operations, including AI techniques, renewable energy, storage, and microgrids. She has been active in IEEE Power and Energy Society and served as IEEE PES and IEEE PES President in 2012 and 2013. She is an active she's an IEEE and ASEE Fellow. In 2021, she was elected to the Washington State Academy of Science. Our second speaker, our co-speaker today is Dr. Vince Sprenkle, who joined PNNL in January 2001 and is currently Technical Group Manager for the Electrochemical Materials and Systems Group at PNNL. This group is focused on the development of the electrochemical materials and systems for advanced energy storage and conversion applications. He is also currently project manager for the Department of Energy Office of Electricity Energy Storage Program at PNNL. This project is focused on the development of electrochemical energy storage technologies to enable renewable integration and to improve grid support. He previously led other projects in the development of solid oxide fuel cell technology and planar sodium batteries. Prior to his arrival at PNNL, he was a senior ceramic engineer at Lytton Life Support and was responsible for the development of prototype advanced electrochemical oxygen generating system. Dr. Sprenkle currently holds 14 US patents on fuel cells, batteries, and high temperature electrochemical devices with 22 pending patent application. He was named in PNNL Inventor of the Year in 2014 and has been recognized as key contributor on 4 licensing activities while at PNNL. He received a 2009 FLC Award for Technology Transfer of Solid Oxide Fuel Cell Technologies to Delphi Corporation. So welcome both Dr. Schulz and Dr. Sprenkle, and I'll hand it over to you for the talk today.
Okay, so we're going to kind of do, I'm going to do part A, and then Vince will do part B, and then I'll come back and do part C. So in doing this, and I had to put a Go Cougs in for across the state of Washington since we won the Apple Cup. So I had to share that today. So let me see if I can get my PowerPoint going here. All right, can you see it okay?
Yes, begin.
Awesome. All right. So today we're going to talk about UIAssist, which is the US-India Collaborative for Smart Distribution Systems with Storage. And I appreciate Vince being here to talk about some of the PNNL storage activities overall that we've integrated, that we're working to integrate into UIAssist. So as we look at, when we start to talk about resilience and the power grid, a lot of different ideas come up as we're talking about this, particularly the distribution system. We talk about different sources, wind, solar, we talk about storage and its impact. We also talk about a lot of different areas. We've got advanced distribution systems, markets, microgrids. We've got to look at policies, regulations, standards, and technologies, how they integrate, as well as energy management. We also have the protection and sensors and the cyber physical interactions with cybersecurity. Lots of different aspects of that. And then in addition to all the technical side of things, we're also looking at how do we prepare a workforce and what is the social acceptance and impact. As we look, as we talk about resilience, as we talk about these technologies, and even as we talk about cybersecurity and privacy, there are issues that come up that people are unsure. And so one of the things we start to look at is how do we get simulation tools, how do we get benchmark systems that we can test and do some of these algorithms and activities, then go into lab demos where we can do hardware in the loop, controller in the loop, and then finally go out into the field to test these. And when you start talking about this, and then when we add the international perspective, what are the similarities and what are the differences we see across? And this is really what we're talking about when we talk about UIAssist. These are a lot of the topics that are part of that. So there's obviously in the seminar today, we can't cover everything, but we want to give you a snapshot of some of the different activities that we're doing. UIAssist, so US and India have several joint partnerships that in 2010, there was actually between the State Department and India, there was a MOU. In the first phase, there were 3 centers. There were smaller focus centers on solar, biofuels, and energy efficient buildings, or smart buildings with what we would call it today. Then in 2016, there was an announcement, and in 2017, UIAssist was funded. It's a $30 million project over 5 years, which is now extending to 6. And then we're looking at 15 million in the US and 15 in India, with half of that coming from the US Department of Energy and half of that coming from the government in India, DST, Department of Science and Technology. So when we look at UIAssist, let's talk a little bit. It's the project, as I said, is jointly sponsored by DST and DOE, as well as supervising support from the Indo-US Science and Technology Forum for this project. And you can see here as we look at a lot of different partners that are involved in this. So as we look at this map, we can really see the different partners across India and the US. In the US, WSU is the lead. We are working with academic institutions such as West Virginia, MIT, Texas A&M, and University of Hawaii. We're also working with 3 national labs, PNNL, NREL, and Lawrence Berkeley. We're working with utilities, regional utilities, including Avista and Sonomish PUD, as well as NRECA that looks across rural electric co-ops. We have also some consultants in Burns and McDonald, and as well as Venkata Systems. So as well as software vendors that are working with us, ETAP and others that are here. So L&T providing batteries and so on. So it's a large project with a lot of moving parts. And you can see on the India side, we're working with 5 different IITs, as well as both utilities and industry in India. So as we look at these objectives, we're really looking to evolve distributed energy resource penetration in a sustainable electrical system. And how do we optimize the placement and management utilization for a secure system? How do we also look at how do we do controls when we have either a microgrid or advanced distribution system with a lot of storage, or both dispatchable and non-dispatchable generation? And then how do we look at demonstrating the cooperation across and multiple different levels here that we see in this particular graph, as we're looking at also the interaction between transmission and distribution and what happens there. So as we look at UIAssist, basically we're starting with looking at a lot of different tools coming out of this project. Obviously, with 6 years and $30 million, we're starting with the research side, where we are doing the algorithms, the data, the test systems, and then from there we're going to go into the test beds and then the prototype and field demonstrations that are there. And this just shows some of the different areas that we have, and we'll talk more about those different areas. And but these are some of the outputs that we expect, as well as the international collaboration and partnerships that have been developed over the 6 years that we can leverage in the future. So here we are talking about, we have what we call themes, where we broke it down into different research areas. And a couple of the different themes that we'll be talking about energy storage today is looking at different aspects of that, but also looking at the controls aspect and protection, looking at cybersecurity, which included both cybersecurity and protection of detection and preventative measures, but also cyber infrastructure. What kind of sensors do we have? What kind of communications do we do? Then looking at how do we start to pull all those together? And then finally looking at markets and regulation. And we have these bench test systems over here that we talk about related to that we're looking at, where we're just using systems that already exist, pulling in our field test demos and going from there. And there's some other different aspects we'll talk about. So and then the 8th part is the pilots and the lab demos, and then we move into actually the field demos, and we'll talk a little bit more about those. So here's another one that kind of shows the relationships between the inter-thematic relations, because really things can't happen. Storage doesn't happen in a vacuum, but storage is part of looking at both our field demonstrations. Looking at relationships related to our DSO functionality, looking at our measurements. All of these kind of interact together, and we see the different aspects, and then all of those feed into our field demonstrations that we'll talk more about. So leveraging teamwork. So one of the important things in this project as we look at that is how we're working together with multiple different partners. As we said, a lot of different partners here. And I just highlighted in particular how we're working with PNNL, WSU and PNNL are working together on system level battery models and working with that. And we're very fortunate PNNL has a lot of experience in that area and is able to add to our different projects, as well as we've seen things grow out of other projects they have where we can leverage that data or leverage that partnership for some of our additional work. And we'll talk through as we go on here. We also have the India partnerships where our India partners are working together. And then next we have our India-US partnerships. And in theme 3, PNNL has been working in multiple different areas to help us with this. And that's what we're going to have Vince talk a little bit about in a minute. So now I'm going to open it up and let Vince talk a little bit about some of the storage activities that we're using and interacting with for PNNL. So I'm going to stop sharing, and hopefully, Vince, you can share.
Yeah, let me try here real quick. Am I still coming through okay? It looks like it changed my connection here a little bit while we were going.
Yes.
Okay. So yeah, thank you for that introduction. One correction, I noticed I did send the wrong bio. I am no longer the group manager of our energy storage group. I am moved to a senior strategic advisor, and Jay Schall is now our group manager of that. So sorry about that error in the bio. But I kind of wanted to present, as we're looking at this, and I appreciate the comment on teamwork, because there's a lot of things that go into understanding how to effectively value storage, how it needs to be deployed, and it's more than one individual entity can do by itself. So hopefully, as we kind of go through these slides and give a background of, where we're drawing from some of that experience that goes into the UIAssist and where we see this growing, kind of our knowledge base as we move forward. So with that, I'll start through. I did include a couple of background slides. Sorry, folks. Here, just to go on PNNL for those, this will not be anything new for all the PNNL people online, but try to do this quickly. So PNNL is one of 17 national labs within the Department of Energy complex. We are an Office of Science lab, and so that mission does present us with a broad mission that PNNL can work on. And so if you look at that mission, we are really focused. We have a large part of our portfolio that's focused on nuclear materials, threat analysis, fundamental science related to chemistry, earth science, data science, and biology. And then where our energy storage portfolio really comes into the energy and environment sector focused on decarbonization. And so energy storage is a major thrust area at the lab and has really significantly grown here over the last decade or so. Overall, PNNL, and we are about 5,000 staff, about $1 billion in contract research. And then as an Office of Science lab, we are heavily into publication and disseminating that information and lessons learned from the research out to the overall community, and in capturing some of those inventions and getting those out and commercialized. And so you can kind of see some of the metrics there. The pie chart just kind of gives you a breakdown in terms of the different directorates that we have, where our energy storage work is based primarily is in the Green Energy and Environment Directorate. So just a little background on PNNL, and now I'll try to focus on the energy storage work. So really, when you look at storage, you are focused on two things. We're really focused on understanding the cost. We understand fundamentally that the cost of these storage systems has to go down so we can get ubiquitous deployment of storage throughout the infrastructure. But we also have to understand what's the value of storage throughout the entire system, as Noel mentioned. So whether that's at the bulk energy level, through the transmission, through distribution, or behind the meter residential storage systems. And again, here I'm focusing just primarily on stationary energy storage. Some of the things, and why this is a simple graphic, it's important to understand everything that goes in there. And so if you look at cost of a system, we see press releases every day that come out and say, oh, here's the cost of lithium ion has decreased. That, in essence, is one small part of the energy storage system. And so you've got it at a device level. You have to have supporting things in there. And this is what that chart down below here tries to show. You've got that basic, what we call a storage block, or your fundamental device. You have the balance of system that makes that DC basically system function there. But then that has to be integrated with the power electronics, the controls and communications, systems integration before you really get to an energy storage system. But then to put hardware in the ground, you have cost associated with the engineering, procurement, construction, project development, grid integration. So all those costs need to be captured as you start to look and evaluate whether or not this is going to make economic sense for a deployment. Then you have to look at what are the overall operating costs over the lifetime of that system. What's the fixed O&M? What's the variable O&M, where warranty considerations, insurance, all that gets factored into whether or not you can make money or provide net benefits with an energy storage system. And then another thing that we're starting to see as this industry is growing is a bigger look at what are the decommissioning costs? What's the end of life considerations that need to be taken into account? If we look at a high renewables penetration scenarios, and we have widespread distribution of energy storage throughout the grid, what are we going to do in 10 to 15 years when these systems start coming offline? And what are we going to do with them? And so now we're starting to see a lot more research into what are the end of life considerations, and those cost elements have to be factored into the overall economic evaluation. And so if you go to the next level, what's really key about this is, from our R&D perspective, is using that real world analysis from these field deployments to really try to drive the R&D agenda. And so once you know how it needs to operate to obtain maximum value, you can start designing systems that will deliver better value for you, whether that's in a redox flow battery and improving the round trip efficiency in there, or lowering the auxiliary losses on a flow battery so it can perform at some lower levels. Or sodium that doesn't have supply chain constraints, or zinc manganese dioxide, which is a primary technology we all know in our AA and AAA batteries, but to date has not been reversible. So if we can do the research on there to make that system reversible, we do have a cheap source of technologies. And so those are just some of the technologies that at the lab we are working, but it is informed by that end use and how we need to direct it, direct the technology. So the technology development is, again, a small part of our overall portfolio. And I think what we bring to the table into this partnership with WSU, safety and reliability is another aspect. So we're both working with industry on how to, are the codes up and are they the best codes that we need to ensure that these systems, when they go out, are safe to be deployed within public areas. We look at reliability. And so one of the things we have is a reliability test lab where smaller scale systems are put through simulated grid duty cycles so we can accurately track that performance, understand what the predicted lifetime is. We work with regulatory agencies across the country as they're exploring, how do they incentivize storage? What makes sense based upon where the state of the technology is. And then where I'm going to focus today is what we call our industrial acceptance. And that's where we go out and support the field deployments. And this is really where we intersect with the UIAssist and WSU on this project, is that knowledge of it and what we've built up to where you are bringing the physics of the storage system into understanding the economics of it. And I see my colleague Dee Wu is on here, and so Dee's been leading this effort for us, and so I will give it, but we'll have Dee online if we have any questions as we go through. At the heart of that industrial acceptance has been what we call our energy storage evaluation tool. And this is really a suite of applications that enable you to start making those decisions about what's the optimal dispatch that you could look. And a lot of these times we are looking at perfect foresight on these systems, but it gives you that first kind of evaluation of whether it makes sense. A lot of times we go into a field demonstration understanding that a single application will not make the economics work. And we have to be able to stack the benefits of it. So you are doing multiple services with an energy storage system to get optimal value. Well, as you start getting competing services in there, you have to understand when it is the correct time within that storage system to be dispatching for that application. In certain cases, you could have, for example, in a flow battery, where you've got auxiliary pumps and maybe a larger auxiliary load in there. If you are in a low state of charge of the battery, you have all those costs associated with it from the auxiliary power. It may not make sense in certain applications for you to dispatch under that condition. And that's really what we try to get at, is given the technology parameters, how do we optimally go through that? And so that's really we see in that battery storage evaluation tool, the microgrid asset or mass score sizing tool. We've evaluated and expanded this to start looking at hydrogen storage as people are starting to look at that as a longer duration storage technology. And of course, as we know, the biggest number of storage capacity we have in the US is pumped hydro in there. So that tool, and there's a link there if you are interested in that. And I got a few slides just to kind of show you some of the examples. One of the first ones that we did was working with Portland General Electric on the Salem Smart Power Center. So that was a 5 megawatt, 1.25 megawatt hour lithium ion system that's installed in Salem, Oregon. And really started looking at how do you stack benefits? And that system was purchased for a single purpose in terms of trying to do frequency response. But now, what's the availability of that system? If there's more availability in there, can we get other services from it? And so generally that system could look at about a $264,000 annually from just providing frequency response. But if you start stacking some of these benefits and starting to look at demand response and spinning reserves and VoltVAR support and adding that into there and not violating the overall physics of the battery, you could derive about $170,000 additional value from those stacked benefits. So nearly doubling the amount of benefit from that storage system. Another one that we worked with was with National Grid on Nantucket Island. And so they have 2 underground transmission, but they are a summer peaking facility due to the tourists there. So for 3 months out of the year, they have a peak load on there, and we're going to need a 3rd transmission line in order to supply that system. Well, they looked at what could a system of storage plus a combined cycle system work to offset or defer that transmission line upgrade. And you can see here on that pie chart in orange is basically the revenue requirement you would need to break even. Most of your benefits do come from that transmission deferral there on the left that's in blue. But one of the keys, this is only being used primarily, that deferral service, for 3 months out of the year. What do you do with that storage system the rest of the time? And so there you can see another almost $40 million in services a year you could get out of that system during the non-peak time. And in doing these, you take into requirements of what the utility needs. So in this case, about 50% of the stated charge of that battery needed to be reserved as a resiliency requirement. And that was specified by the utility. And so we worked that into our calculations to understand what the overall economic dispatch is. I'll give you one more. Example 3 is our work here now with NRECA on some resiliency assessments. Several of these are military installations across the country. Several of them are more with co-ops trying to support their members in there, like in Hyde County, North Carolina, and Red Feather Lakes community in Colorado with Poudre Valley. And so that's a wildfire resiliency center that they've got, and just trying to understand what is the ideal size and duration of storage to provide that resiliency benefits. So one of the keys is we can go through, we can look at this, we can do an economic assessment. But I think, as Noel mentioned earlier, one of the keys is taking this research, taking this understanding of the battery and how it needs to be used, and turning that into a realized dispatch strategy. How do you do the controls and communication so you can get this out? And so that's one of the things that we look forward to in this collaboration, is being able to elevate this more from just an analysis, and how do you move it into a control and dispatch as we move forward. And so that's I think one of our key metrics, and expands what we're trying to do at the lab in able to enable greater storage deployments in the future. And so here you can just see these are some of the deployments across the country that we have supported, and several of those now we brought into UIAssist to help out there. I think, as Noel mentioned earlier, with Snohomish PUD, Orcas Power and Light. And so we can together kind of expand our working knowledge of that system. And so with that, and then one thing I wanted to point out, we are looking at, in 2023, having a new facility at PNNL called the Grid Storage Launchpad. And what that is really focused on is providing a mechanism so that we can validate these new technologies faster and get them out, so we can actually impact a 2030, a 2035 high renewables penetration scenario. And so working as, working in a team and getting how these systems are going to be used and what are the needs are is critical for us to be able to get this facility to work, because we need those use cases to filter in and help really direct the R&D. And so that's one in the future that we really look forward to enhance collaboration to help drive that and make this successful. So with that, I'll stop and turn it back over to you, Noel. Thank you.
All right, thank you. Let's see if I can make this work here. All right, so thanks Vince, for talking through some of those different activities. And I think what's neat is we're talking about UIAssist, but PNNL and the storage angle are involved in several different Clean Energy Fund projects together as well in the state of Washington. So one of the neat things is the ability to leverage these activities, both federal, state, and other projects that we have to really be able to make 1 and 1 greater than 2, which is one of our goals of AGI. So now I want to talk through some of the different high-level scientific and technical highlights and that WSU has been involved with, as well as some that PNNL is involved with. So with that, hopefully, yeah, there we go. So first, the field demonstrations. These are, we're kind of beginning with the end in mind here. This is our final output, is how to do these demonstrations on here. And you can see some of the activities related to the rural NRECA that's been working with PNNL, some activities there, looking at some of the different activities, and we'll talk a little bit more about that. We then have our partners over here in India, and I'm not going to go through all the India ones because of time constraints, but I did want to mention this particular one that is really a rural pilot, and rural, much more rural than we think about in the US, but this is actually 2 hamlets that are being electrified for the first time. And they're being both with biomass as well as with solar power, and they are connected to the grid, but the power is not reliable. But one of the interesting things that we're doing on this project is we're working with PNNL on these battery models to be able to do some modeling and simulation of these, and then we will take the data that we get and compare it to the actual numbers that we have coming out here. And this is one of the great things with this project, that it enables us to compare the simulations and the real world work that's out there. So this is an example of how we're working with India, WSU, and PNNL, as well as others, to work on this particular project and this particular setup of these microgrids and things that are happening in there. Some of the US pilots, as we've got a battery coming into Pullman, and in the WSU Pullman campus, we will have a battery, and we'll be using a microgrid related to that. And we're working with L&T for the battery. We'll be working with WSU facilities on integrating that, particularly for some resiliency related to some critical loads in their facilities that help some of the controllers and things like that. We also are working with Avista on the Avista in the Spokane, and looking at both distribution markets as well as distributed VoltVAR control. And we're fortunate that Avista has both a test system that we can play with as well as a lab system that we can play with. Texas A&M is doing some work on transactive energy and looking at kind of the building aspect and some of the different aspects of EVs. And then as Vince mentioned, we're also working with both SNOPUD and Opalco and some of our interactions with PNNL that they've had to try to leverage that data and look at how we can take the analysis of what we're doing in UIAssist and compare some of our modeling simulation to what we see there. This is another aspect. This is kind of going more on some of the other WSU activities that we're doing, as one of the important things is trying to look at how do we integrate the cyber physical. And this is kind of looking at some of our activities on theme 2, where we're doing test cases, as well as looking at themes 3, 4, and 5, where we have storage, where we have protection in the cyber physical aspect of it, and controls, as well as theme 5. So in this particular case, we're looking at going from what we would have offline to real time to our field pilots, but also creating some synthetic models so we can compare apples to apples related to some of our algorithms and work. And then on top of those physical models, putting our cyber physical on here to be able to work together on that. And that's one aspect. And this has a lot of different partners involved in it related to this particular part of that, and universities as well as other partners. The other project we have is working on the ADMS MEMS. So basically looking at the difference between the advanced distribution systems and the microgrid energy management systems, and looking at some of those relationships there and the interactions that we have there. And this one's a project we're also working with India on, related to validating the microgrid model and looking at protection, as well as looking at the algorithm for power scheduling in the nanogrids, and then trying to look at DC, how do we control that related to DC microgrids. And you know, that's a different aspect of something, and something we're able to do by having multiple partners is explore something. Even though we don't talk a lot about higher voltage DC grids in the US, there's some opportunities for that in India, and some lab test demonstrations we can use. We're also looking at some resilience tools and looking with that on some of the different partners that's pulling data in that we can use, and both the computer science side of things, as well as data analytics, looking at machine learning and activities, as well as the outputs of tools related to resiliency, and also metrics based for cyber physical security activities, and having the interfaces that relate to this. So we have the simulation and the analysis behind the scenes, and then we have the interfaces that allow us to be able to get that data and look at that in more detail. Another aspect that's data driven is looking at how do we, load profiling, and how do we look at behind the meter loads and look at disaggregation of DERs. As we look at a lot of solar on rooftops, how do we differentiate that and how it's impacting the grid? How do we look at forecasting? This is University of Hawaii doing some work related to using cameras and forecasting day ahead, hourly, as well as minute interval data sets to look ahead. How do we visualize some of this some of the radiance and solar activities, as you can see in this irradiance going on Oahu, and looking at those, and looking at machine learning to help analyze these techniques and get an algorithm to work with event analysis, as well as looking at model predictive control for distribution systems and AI distribution restoration. So we're looking at, another interesting part about UIAssist is not just the power systems, but also integrating a lot of our colleagues in both controls as well as computer science and in different aspects of this. Excuse me. One of the other areas we're doing a lot of work in is looking at VoltVAR Control with the enhanced DERs. And if you look at this, we get a lot of different aspects. We've got centralized, decentralized, distributed, holonic, hierarchical. You can talk about all these different algorithms and what kind of information is needed, what kind of information is collected, and working across multiple different faculty and students across the three different universities. We're looking at these algorithms, and we're moving towards working on these where we actually compare them on the same systems to see what evaluate what the strengths and weaknesses of each of the systems, and see how we would work together with those and possibly implement one of those related to our Spokane test system. So lots of different aspects here on the VoltVAR Control. We're also looking at markets and working on the market and regulation areas related to MIT's doing a lot of work in this area, particularly looking at the interaction of DSOs and TSOs. How do we look at that from a market perspective, as well as Texas A&M doing the nanogrids. WSU is also looking at distribution connected resources. How are they part of both federal and local regulations? How will they overlap? How do we interact with something that may be a microgrid or source on the local level, but then also could contribute to a higher level, as well as the transmission transactions that are happening. So a lot of different aspects related to that in this project as well. This particularly shows, in addition to our physical test systems that we're working with our utilities, we also have some test beds where we can do hardware in the loop, controller in the loop, real-time simulation of a work that we're doing. And you can see at Texas A&M, they've got an Opal RT where they're doing some simulations related to validation and verifying some of the models we have, some of the algorithms. WSU with our RTDS equipment, basically looking at some of the different layers, and also Opal RT that we're working with. NREL actually has some large test beds that will enable us to do some work on testing different aspects of this, including possibly some of our storage modeling that we have related to different parts, different test cases. And then Hawaii also has a test bed that they're working with that has opportunities for us to look at real data and integrate it with the different systems. And then Burns & McDonnell has a smart grid lab that really enables us to look at not only the power systems, but communications and cybersecurity aspects as well. And those are some of our activities that we're pushing into right now as we go over the next year, related on how do we do the R&D we've already done, how do we pull that together and get that to integrate that to be ready to go to our field demonstrations. This just shows some of the US-led achievements that we've had to date. The transactive control nanogrids, the retail markets for MIT. Also, Hawaii's been instrumental in the forecasting, PV forecasting tool. WSU has been working with the real-time simulation, the resiliency tools I talked about, as well as our cyber physical SysNet, which will be the tool that we could do. And then we're also working with NREL and WSU to look at a testbed that we would also work with India on having a distributed testbed where we could work together on having integrating across multiple different systems across multiple partners. So what are the project impacts that we have as we start to talk about UIAssist and what we're doing here? You know, one of the things that we're really trying to do is look at how do we come up with these solutions, whether it's advanced distribution systems or microgrids with renewables and storage in multiple settings. We're not just talking about urban or rural or what we call semi-urban, but looking at the different settings and how do we improve the quality and continuity of power supply. We want to look at resiliency and reliability, and as we're aspect of reducing our carbon footprint, which obviously has become even more important. We're also working to look at advanced concepts and how do we help improve for existing professionals? How do we help them understand some of these new technologies that are coming in? How do we provide training and for them, as well as providing the public with information on awareness and policy intervention? And obviously, as universities, we're also working on the next generation power professionals that we have here in the audience, and looking at how do we work across different partners. With 15 partners in the US, we've got partners that are national labs, universities, industry, we've got consulting companies. It really helps us give a very different perspective of some of these issues, but it also helps us bring in experiences from way beyond just what we're doing at this project that we can add to that, as well as our papers and then short courses and other things that we're doing. Some of the immediate impacts is basically we're getting a lot of overlap between our 9 universities, and that's providing opportunities for understanding global perspectives, but also exchange in classes. We have guest speakers in classes in both places that we are able to share and share different information. You know, we've created this large team of about 30 entities to all work towards this common goal and taking different bits and pieces in that. And the other interesting thing is the public-private partnership, as we've had some of the different partners as part of our platforms, as well as our support and our matching. It enables us to come with different perspectives. It's not just an academic perspective or a utility perspective, but we're combining those, including new technologies, and how do we integrate those. And also looking at how do we create the next set of Indo-US energy energy solutions working together. And then last but not least, but really cool, is that we've electrified these 2 Indian hamlets that didn't have electricity before. And as part of this project, not only are we providing the electricity, and we're also understanding it and using it as a platform to learn more about the rural aspect, which is a little different in India than it is in the US. So beyond, we're continuing on these solutions, and the field demonstrations, we really feel the next 2 years are going to bring a lot more to light as we move forward on these and look at how we integrate these solutions with publications, presentations, and other activities, and also find other ways to leverage what we're doing with other partnerships. And I'll talk a little bit more about this. So one of the things in September, the US and India, they had a discussion on the strategic partnership that they're having related to strategic clean energy partnership, or SCEP. And these are areas, if you look at UIAssist, basically we've gone from 30 organizations into one team, that now we have a lot of the tools and things in this area that this is what we're committed to for the future related to that. So, and then here we have our, combining other researchers and other projects into this, and how do we advance our portfolio in moving forward related to that. So with that, I'd just like to say thank you. This is an example of some of us visiting either India or the US on this team, as well as I'd like to acknowledge both the US Department of Energy, the Government of India, and DST, and then the Indo-US STF for their support of this project. So I think with that, hopefully I can stop presenting. Stop sharing. There we go. And see if there are any questions that we can try to answer.
Thank you, Noel. Thank you, Vince, for the presentation. So I'm not seeing any questions on the chat. I'll ask students to unmute myself and speakers to, attendees to unmute themselves and ask questions if they have any. Okay.
So I have one for Vince. So Vince, you've got the picture of the grid storage Launchpad. How do you see that in general being a resource for WSU and AGI related to next steps on storage, as you talked about being ready for 2030?
Yeah, thank you for that. So what we're looking at with the grid storage Launchpad is being able to take that that user information and distill it all the way throughout the development cycle. And so in that, we are going to have fundamental material science tools that are open to collaborators. So to WSU, if you need to come over and use some specialized equipment, we would have that. We would have in there, we're going to have the ability to prototype in different formats and different technologies. But one of the things I think that is most interesting is we are designing this to have what's called a fellowship lab. And so this is to take those best ideas that are coming out of the universities across the country, out of small businesses, and a way to incubate them in a storage-centric environment and have access to those tools. So I would look at that as we get into it. We're trying to set up to have 4 labs in there, and so one company or a new idea could come in, have their private facility that they can develop their new material or technology in there, but then be able to bring it out into GSL, apply it, understand the use case, and get to a level of validation that they can go out and get that next level of financing and move forward. So I think, in terms of just scientific collaborations, we're hoping to do that, but also through this fellowship laboratory, really be able to kind of spur that entrepreneurship that's coming out of like WSU and other universities.
Great, thank you.
Yeah, that's a really interesting resource, exciting resource for us to have and work with the storage-centric solution. So that's excellent. Thanks, Vince. I'm still not seeing any questions, so I'll go ahead and ask one I have. So this is for you, Noel, on demonstrations. So it's really exciting to see the field demonstrations that you have set up for this project. Can you talk a little bit more about those field demonstrations and what are the unique challenges when we go from, paper kind of work to actually demonstrating these technologies out there in the field?
Yeah, so that's a great question. And the field demonstrations as faculty, we're learning more and more. We do some of that in some of our projects, but trying to work with WSU facilities, and we've had to find a location. We've had to see what resources they had there for trying to for communications and modeling and some of that. So there's just a lot of other things we've had to work with. We're very fortunate that Avista has set up this microgrid as part of the Clean Energy Fund project that really is a place where we can play. And that's what I took some students earlier this month there for, that's basically what Mike Diedisch said, is it's a place where we can try things and we can separate it and look at things. And it may be at 3 a.m, but at least you can try some things. And that's really, I think, where the rubber meets the road with these projects, is how and where DOE wants to see us. As faculty, we do a lot in the labs and simulations, but then how does that relate to industry, and how does that really benefit industry? And besides any seminars we give, but actually seeing some things tested out. And the other thing, because our utilities have been involved from the beginning, is they'll kind of ask questions about, well, why are you doing it this way or that way? Or have you thought about doing it this way? Or that's not going to work because we don't have that data available right now, and some of those kind of things. So the fact that the demo is the final part of it really helps us be able to try to pull in across the board all the different perspectives, versus if we kind of, as universities, worked on it, threw it over a wall, and then some other people are working on it, threw it over a wall. As a team, we've had a lot more interactions. So those are some of the challenges. Also, as making sure we don't mess up something on a real test system that could cause an outage or something like that. So doing a lot of due diligence on that to validate and verify before we go into an actual setting. And in some cases, what we're doing with the field demos is comparing simulation to what's really happening. In other cases, we're hoping actually to have interaction between our algorithms and what's going on.
That is excellent. And I think that's really needed for in us to convince the industry that yes, what we are doing is useful and it can be done. Yeah, that's excellent. So I have a question to both of you, actually. This talk focused on different aspects, but one of the major point was on the storage, right? So what will be your feedback or input, or maybe just comments on, as power engineers, how we should be looking into how the things are changing in storage? And power engineers, I mean our upcoming graduate students, what point of nugget of knowledge you would want to give them about how the space is actually coming up?
Vince, I'll let you go first.
Okay. Yeah, I'm trying to think about that, and it's a little out of my field. I'm a material scientist, but one of the things that we see, especially from like a power electronics aspect, that impacts our overall cost, is a lot of the technologies that we develop. We want to develop systems that are safe, and so they're water-based. And by water-based, you are limited by the voltage that you can do. So a lot of these new technologies are coming out very low voltage, and the power requirements to do step up to line voltage are a lot more aggressive than they are with like a typical lithium ion. Lithium ion, each cell is about 3.7 volts, whereas we're limited to about 1 volt. And so we see, as we go through, a new technology that may be safer has a higher cost of power electronics to get it to integrate with the grid than the de facto standard of lithium ion. And so how do you get those step up transformers and DC-DC converters to be more economical, I think is a real opportunity as we look forward in there. So that's more from a device level looking at it.
Yeah, and you know, I think storage is going to be our key as we have a more and more non-dispatchable loads, as well as generation. You know, in the mix, storage is going to be the you know, the glue that holds all that together. And you know, we continue to try to find a storage that's cost effective. You know, that on the high level that we talk about with utilities, and we're making some progress in that. But really, as we talk about microgrids, as we talk about resilience, storage has a place in all of those related to helping keep the things balanced that we need. And so I think, you know, and Vince brought up a great point about the power electronics, but I think also we're seeing with the storage and with the data is the data science and the AI integrating into the grid. And that's becoming a much more important part of how we do controls and algorithms. And so as a researcher, having some background in that is going to help you in understanding the big picture. You don't have to be an expert, but you want to be able to communicate with those that are in that particular area, or be able to think about how your solutions might use that. So I think, you know, that would be my comments about storage.
That is great. Thank you both. Actually, it just brings a very a little bit out of the scope question, but we are over the hour. But maybe, Vince, I can bug you just slightly on this. What are your thoughts about liquid metal batteries? I have been seeing a lot of, you know, interest recently in this area. What do you think are the potential for the grid storage?
Yeah, I think that is one of those that's coming out. We're all looking for solutions that, you know, we can get more storage capacity than what we have today. And so that does offer an opportunity to be able to store large volumes of there. You know, what we've seen before is, you know, the challenges are you're dealing with high temperature, you're dealing with corrosive metals, and so you have to solve some of those fundamental materials issues in there. But if those can be overcome, then yeah, they do offer the potential to start looking at how do I move from 2 to 4 hour centric storage solutions to this 10 to 20 to week long storage solutions that we need. And it is going to require something different than what we have today. And so, yeah, liquid metal batteries are there. There's a whole slew of different technologies that are trying to focus on that longer duration part of the market in there. So.
Thank you. Thank you both. This was a very interesting and insightful talk for us. Thanks so much for speaking with us today and for spending time with our students. We are 2 minutes over the hour. Thanks so much for answering all our questions, and we'll call it a day today. Thank you, everyone. Yeah.
Thanks,
Noel. Thanks, Vincent.
Thank you. Take care.